As far as the test goes, again, it's a short test. Okay, I'll tell you now, it's only a total of, I think, 40 points on the test. It's a 40-point test. So there's only like 4 multiple choice, like 2.5 of those short answer in the middle. And then for the math parts, there's, I think, 3, choose 2, or I think I make you do the first one and then choose one of the next 2. Forget which way I set it up. Okay, but there's only a few problems. It's on the lab from chapter 6. What was that lab about? Who can remember? Whoever just handed it in. Yeah. What was that? Momentum. Good. So the lab on momentum. So the stuff from that you should know is the theoretical stuff. It will not be mathematical. I already tested you, a lot on the mathematical component of momentum. So it could be like a multiple choice or a short answer. So knowing the idea, let's see. When things collide elastically and bounce off each other, they're not sticking together, so there's no energy loss. When it's elastic, they stick together, it loses energy due to fusion. What else? If there's a momentum before the system, there's momentum after. If the net momentum beforehand is 0, like if they're equal and opposite, and they collided, they would just stop, obviously. I'm just trying to think of all the theoretical stuff we talked about with momentum. If 2 people start at rest, and they push off each other, right? They have 0 momentum to start, so when they push off each other, they must have equal and opposite momentum afterward, right? So they can cancel still. So if we push off each other, if I'm bigger than the other person is going to move faster. But if I'm smaller than the other person is going to move slower. But we still have equal and opposite momentum because we started with 0 momentum. Or 0 momenta, I guess, the word for the 2-body system. Okay, that's lab 6. Then what was chapter 7 on? What was chapter 7 on? What was the idea? We had 2 topics within chapter 7. What were they? What were the 2 topics? James?
Circular motion and the force of gravity between 2 bodies.
Are you writing an outline for the test?
Say again?
What are you writing?
Just the 3 things there on the test. That's all there is. That's why I'm just mentioning them, and then we'll look at a few problems. So circular motion. What was the idea behind circular motion? Who can give us a quick overview? What was the idea behind circular motion? You can think about the cup as your example. That's the one we did to start with. But what was the whole idea behind it? Justin.
The object that's on the screen, or
That moving in circular motion?
yeah, it wants to move it into space, but the tension of the string is...
Hold on one sec. I'm hearing like noise. Can somebody just check if their phone is going off by any chance?
It's a radiator.
Is it the radiator, really?
Yeah.
It's so loud. Okay, keep going.
Yeah, so within the tension of the string, wherever it's holding it, it's keeping it within the...
Circular motion.
Yeah.
Now, what happens if the centripetal force that the person's body exceeds the strength of the tension in the string? It breaks. Okay? Just like a car going around a racetrack. If the car drives too fast, the velocity keeps going up. That's a higher centripetal force. So that centripetal force, if it exceeds the force of friction the tires can withstand, the car will slip off the track. James, you mentioned something yesterday to me. What was that again?
That's actually how they measure like a car's road holding is they drive it around a circular track at higher and higher speeds until it begins to slip. And the moment it slips, whatever the G-force it was under laterally is the road holding.
And that's exactly what we've been doing. Remember what I've been saying to you? Find the G-forces based on the acceleration that we get? That's what James is talking about. That exact thing. So what they're doing is they're saying, well, at what point does the car begin to pretty much fail its objective? The objective is to, travel from point A to B. When it starts slipping, it fails. So they're looking for that failure point. And then what do you think they do as far as cars go? Like, obviously, cars that are going to be used by consumers versus cars that are race cars. I mean consumer cars. What do you think they do if they realize that with this much velocity, with a radius of this much, and a mass of whatever it is, it starts to slide? What do you think they do when they make the car then as a result of that? Think logically.
Put more torque in the tires.
Okay. So they do something to alter it.
Just try to get G limit up to a point where a normal civilian probably wouldn't exceed it.
Exactly. In general, that's what they're doing. That could be specifically something they do, but that's what I was asking in general. What they do is that they model the car so that it wouldn't get up to that value, right? It's called putting in a factor of safety. It's like, you know what, this desk, right? When we buy these desks, when we shop, because next year there's going to be new science labs. So when we're looking for desks and stuff, they give you ratings. It'll say the desk can withstand X amount of force. So it can hold, you know, like 600 pounds of force. So maybe 3 people could be sitting on this desk and it wouldn't break. Now, it could probably hold a lot more than that, but they account for a factor of safety. Have you ever gone on an elevator? What does it say?
Weight limit.
Weight limit. What do they usually say on elevators? Well, newer ones. The older ones might be different. But what's a weight limit in an elevator usually?
2,000.
2,000 pounds, right? About 10 people?
2.5 Tristans.
Okay, 10 people. So, the factor of safety there is huge. Huge. In reality, and I'm going to say this off the record, I'm not telling you to pack in an elevator, so don't do this. Understand? Thank you. But in reality, 15 people, or like 3,000 pounds, could easily be transported in an elevator. And it's not going to break, but they're accounting for that on purpose. So that, you know what, we'll say 2,000, so that just in case for a freak of nature one day, and like 1,995 pounds are in there, and it breaks, they're going to get sued or something, right? Because they advertise 2,000 pounds. So they say 2,000, when in reality, what do you think it could hold? 3, 4, probably 5,000 pounds worth of weight. So when you design things in engineering, you look for factors of safety. So this idea of circular motion and G-forces is what James mentioned yesterday to me in class, and I said to him, just hold on till tomorrow, because I knew it was a good thing to add on, because it's a good application of this. But they're always going to account for a factor of safety, which is why you take these ratings, which is why you actually measure these things. How about the third thing, the force of gravity? What's the force of gravity? Somebody give me a gist, or the gist of that. I heard Tristan from so far, I've heard from James, I heard from Gio once. What about force of gravity? Force of gravity. What did we learn yesterday with force of gravity?
Force of gravity, between two objects.
Yep, it's always between 2 objects.
Well, it's usually dependent on their distance.
Good, very good. Now, Luke, one thing we need to mention is their distance is measured from where to where. And that was the little tricky part. Not just the gap between them, but something else. Yeah, we have to include their radii. So it's from center to center. The distance is measured from center to center for the force of gravity. And Luke is right, it's between 2 objects. So again, include their masses, include their radii. We're going to include their masses also. So for an example, God bless you, imagine the moon, here's the center of the moon. Imagine the earth, here's the center of the earth. There's the distance between them. But that's not the actual value we're going to use for the distance r in the formula for force of gravity. We have to also include the radius of the moon, over here in yellow, in pink, and the radius of the earth in blue. Let me zoom in on that so you can see. Okay? So you have to include these 2 radii in your distance measured. So it's the overall distance measured from center to center. So this is r. Okay? And remember, in this formula, we're going to square r. Don't forget that it is squared. You know, the formula, it's not squared. So that's an easy mistake to make. Okay, so it's measured from center to center. All right, so those are the main 3 topics: lab, momentum topics, circular motion, and force of gravity. What do you want to do to start? Is there somebody's been struggling on? You did your homework last night, so tell me about that. How'd that go? No questions? Everything was pretty straightforward? Some feedback? Nodding? Yes? No? Raising? There you go.
For force of gravity, there was one problem where you had to solve for r squared, or r. In that situation, would you just be able to switch r with
Yes.
FG?
FG. Absolutely. That's all you need to do, and then square root it. So Tristan's question is, I'll come back, I saw hands. Tristan's question was this. In one of the examples, you had to find the distance between them. So the easiest way to do that is just to flip-flop the FG and the R.
Is G in the numerator, or is it multiplying?
It's just multiple.
It's a multiplier. It could be in the front or in the numerator. It's the same thing. It doesn't matter.
It doesn't matter what you do. It's the same.
Think about it, right? If it's in the front, it multiplies the whole fraction at the end. If it's in the top, it's still multiplying by the fraction, but in the beginning.
G times that is the same as G over 1 times that. So
Exactly.
You just combine it.
And the reason the formula has the G out in front, Tristan? The reason the formula has the G out in front is because traditionally in mathematics, you look at a constant in front, or a coefficient, and G is that constant coefficient that's always there. It's not a variable in the problem. So when that happens a lot of time, when there's a constant, you usually put it out in front. So you're going to see later in the year that we're going to look at Coulomb's law, which is an electric field law, and it's K, Q1, Q2 over R squared. And Q1 and Q2 are the charges, and K is Coulomb's constant, just like G is the gravitational constant. Okay? So yeah, you would switch them, and then Tristan just square root it, and you get rid of the square. Okay? Now, what is that R again? Remind me?
Distance between the center masses.
From center to center. From technically, yes, the center of masses. We're going to assume spherical, isotropic, the same throughout, so it's the center. But technically speaking, the center of mass of something like this, see this bottle, is not really the middle. Because clearly there's more mass at this end, isn't there? This is tapered. So there's less mass here. So the center of mass is not down the middle. It would be closer to this end than it would be. Are we all focusing, guys? Okay? It'd be closer to this end than it would be to this end. So we're talking about right around here. So we have to think about that for these problems. It's center to center. So if the problem gave you, let's say the problem gave you the distance between the planets and one of the radius, or one of the radii, and you had to find the other radius. How would you do that? Because it's not directly in this problem. Like, that's not what this is. This is not the radius of one of them. What if I gave you this number, and I gave you this number, and everything else, and I said, find this little radius? How would you approach that? Let's say this number was 1,000, this gap, and say this radius was 70, and we're trying to find this radius right here. And we'll call it R sub 0 for object. The radius of that object. We have the gap between them, we have this 70, and we have the formula. What can I do?
Solve for R, and then you would subtract 1,070.
Exactly, very good. Solve for R, which is the whole thing, right? And then subtract these two, you get what's left over. Remember segment addition postulate from geometry? You're probably like, I hate that. That's what this is. Take a look at it. Why is that funny? Everybody hates it. I taught geometry. No, who cares about segment addition postulate? Well, now it's useful at least. Right? You can actually see an application of it, but I get it. Trust me, I taught
I'll give you $10 for this.
I mean, honestly,
Just walk away, just be like, no one cares.
Miss Starks is teaching me because it's fundamental to other things, clearly, right? You need to know it realistically. But as a whole, it's like, that's common sense. This plus this equals that. But you know what? Until Katie said that, nobody else jumped the gun there. But that's what that was. It's segment addition postulate.
I knew.
Oh, you guys, well, all right. Sorry, I didn't see your hands.
I was just reserving.
Anyway, but the idea, find the overall R, subtract these guys from it, get what's left over, the radius of the object. Okay? James.
So there's another problem with a roller coaster, and it was basically like, what's the force that causes centrifugal motion in it? And I wasn't sure if that would be friction or FM, or both.
Depends on where it is in the loop.
If it's on a rail.
Yeah. Is it inverted? Is it
It
not?
stopped at the top, so like through the first part of the curve.
But it's still moving. It didn't like freeze. It's still moving, but it's paused. Freeze frame.
It stops at the top, but you're
And it's hanging there?
yeah, but you're seeing what the what causes centrifugal motion up until the top.
What are you talking about?
Normal force.
Normal.
Because on what? On the object? On the car? On what? On the person? You follow what I'm saying?
Yeah.
Because the centrifugal force on the person that's reacting is normal force for sure.
Right.
Absolutely.
But
But normal force also, the person not sliding is part friction, so it would be a vector component of each.
Okay.
Like a portion of this and a portion of this summed together. If you're looking at the coaster, it's also part friction, part normal force, but for the coaster it's more normal force because there's very little friction, if anything. But for the person on the seat, there's a lot of friction there, right? So it's definitely friction and normal force for a person, but for the coaster, it's really the normal force.
And then on the way down, gravity is one of the forces. If it's pulling it down the other side.
What's providing the centripetal force on the other side?
Yeah, on the way down.
Well, gravity is helping it at the top, yes. Once it gets to the top, because gravity is now pulling it down. Once it passes this level, like here's the curve, right? Once it passes here, gravity's helping. Gravity's helping, gravity's helping, gravity's helping, gravity's helping. It's really all gravity pulling down now. Some normal force if the centripetal force is greater than gravity. If gravity is, say, 70 newtons down, but the centripetal force felt by the object is 100 newtons, that means the centripetal forces, or centrifugal really in this case, would be 100. The reaction would be another 30 from the normal force. So it'd be part both then. So you could say there would be gravity and normal force on the second leg of the trip. But to answer the question just simply, for a roller coaster, it's mainly the normal force. That's what we answer in that table there. But there are small components of gravity, especially on the top leg, and small components of friction. Okay?
Are there going to be a lot of questions
Friction's part there.
on the test?
Like that?
Yeah.
What do you mean?
Like, what forces?
You should know the table for sure.
The table?
Not saying there's going to be a lot of questions, but we filled in that table in our notes
Oh, yeah.
that talked about the causes of centripetal force.
Oh.
For like remember for a planet it was gravity. For the electron and proton, it's the electrostatic force. What else? The loop-to-loop was lift and drag force. Object on a rope was tension. I don't know if there's any others that we did. Were there anything else?
It was like electro or something.
Electrostatic,
Yeah.
yes. That was proton and electron. That's all right.
Really?
All right, what do we want to do as far as the math problem? What do you guys want to do as far as the math problem goes?
Can we go over the questions that, there was one for homework that you had to find R, and then it asked how, like, the mass changed the force of gravity?
How the mass changed the force of gravity?
Or something like that, like what we did at the end of class.
Oh, sure, yeah. Double, triple, that kind of stuff?
Yeah.
Absolutely.
But I didn't understand how, like, it
Let's
didn't
do
look
it.
like it changed it.
What's so funny back there, you two? So, we're going to look at an example now. Remember the last example at the end of class with like if the distance between the centers doubles, what happens and such? Let's take a look at an example now. I'm going to dictate. I want you to write. Okay? Well, I'll write it also so it's on here. If the... You ready? Good. Okay. If the velocity of an object in circular motion is tripled and the radius of curvature is doubled, what is the centripetal force changed by? What factor, I should write, is. Okay? What factor is the centripetal force changed by? So then we did before and after. Okay, we wrote the formula out once, and then we wrote the formula again with those changes. Just write the formula with those changes. So go ahead and rewrite your formula, but instead of putting just V, put 3V. Instead of putting R, put 2R. So here's our identifiers. The velocity is tripled, and the radius of curvature is doubled. So I've underlined those two changes. So write your formula for centripetal force out, but make sure those changes are involved. And I wrote the normal formula, and then you guys should be writing the formula with the changes involved. Julie?
So when you put the 3 on the velocity,
Yeah, what do you got to do there,
that
Julie?
3 is squared.
Correct.
Times 9,
Yes.
and then the r is just is 2r.
So the V becomes 3V inside the parentheses, and the R becomes 2R. Now technically I don't need parentheses around the 2R, but I'm going to do that just to show that I'm replacing something, okay? And the 3V squared becomes 9V squared. So we end up with what numbers on the top, or what number on the top?
9.
And what number on the bottom?
2.
And the rest is the same, right? So by what factor does it change, folks? 4.5. Okay? 4.5. And does it increase or decrease? Is the top number or the bottom number bigger? Which number is bigger? So it's going to increase. If the fraction, and this is what we were doing yesterday technically, but we happened to get 4 and 2 and reduced it. But this is 9/2. So it increases because this is bigger than 1, right? By a factor of 4.5 or 9/2. Yes. So we're looking at the difference from here to the original formula. The only difference is this 9/2. So this is telling us after these applications are corrected or changed, it's the same answer we got, but multiply that by 9/2. So 9/2 is 4.5. If I take my salary, that'd be great, right? Multiply by 4.5, I'd have almost 5 times the salary. So that's what we're going on here. It's 5 times the force felt, approximately 4.5, really. Nina.
And then just to make sure, if the velocity and the curvature have the same value, like they're both tripled, it cancels out, right?
Well, it did in the other class the other day, but take a look now. Would it really? This would be 3V, which comes 9 still. This would be 3R, though.
Square. Okay.
So it doesn't cancel out here. It would be 9 over 3, right? Which would be 3 for every 1.
Yeah.
I got you, yeah. So it would be triple the amount.
Gotcha.
It only occurred the other day was because, remember, we had M times M in the numerator, and they both changed.
I see.
So that had like a square effect, and the bottom was R squared. That had a square effect. There's a square in the top, but there's no square on the bottom here. Okay? And I did it on purpose with this formula to show you that you can do this with any formula, obviously. Any application at all, you can change it and see what happens. Hey, here's a good application that you should know for real life. When you drive in your car, and most people don't realize this, first of all, how many people have their learner's permit at least? At least your learner's permit. You could have your license. I'm saying at least the learner's permit. How many people have their license?
Luke
Okay.
has the license.
So Luke's very proud of that. So, Luke,
Hey, Luke.
this is a dangerous day. All right. So, when you're driving, Luke, you practice like merging and entering highways and stuff like that, right?
Oh, yeah.
All right. So, as you're going around a turn on a highway, there's something that you should never do, and most people don't realize it. Not never do, but something you should really avoid doing,
Something that
because it makes your car a little bit more unstable when you're going around a turn. No, slow down's okay. Believe it or not, slow down's alright, Luke. Probably shouldn't speed up. That's another thing. But this is something that you don't realize. Speeding up, yeah, you probably shouldn't speed up around a turn either. But you can. It's not going to kill you. But there's something else that really affects your car if you do while you're going around a turn. You shouldn't do.
Turn really sharply.
Sure, turn really sharply, but you can't control that. You're on a highway.
You also can't turn.
You're on a 3. Here, look. Let me give you a diagram. You're on a highway, right?
Well, I'm thinking about GTA right now.
And the highway happens to turn. Here's your car. You're driving in this direction. What should you not do?
Jump out.
Use physics. Use physics to help you answer it too. Think about the formula that we just looked at.
Shouldn't go another lane.
Okay? What should you do at this point? Use that formula. Come on, somebody can figure this out. You guys
You
can.
shouldn't stop.
What should he? Well, you shouldn't stop when you're driving on a highway. Yes, that's true.
Speed up.
No.
Now you shouldn't change your mask.
You have to keep turning the wheel.
Well, sure, you shouldn't change your mask, but I mean, jumping in a car.
More force.
You
Don't
should
apply-
Okay, let's start with that. You shouldn't put too much force in the car. What would cause you to put a lot of force in the car? We said if you speed up, right? Because you'd be increasing your velocity.
You shouldn't brake.
I mean,
What?
that really wouldn't affect it as much.
No, you probably.
Should you not get closer to other
You should
cars?
break the weight right
Tristan,
Should you not get closer to other cars?
obviously.
The mask.
No, the radius.
All right, hold on. Let's pause. All right, the mask you can't change, right? It's a car. You're in the car. You can't change the mask. So the mask has no. Yeah, you can't start. Oh, step out the window. Too much force. Lower the mask so you're throwing stuff. Next time you're littering, tell the cop. Well, the centrifugal force is a little bit high. I'm trying to lower the mask, and he'll be like,
As quickly as possible.
no. All right, so the mass we can't change. How about the velocity? The velocity we said a moment ago, yeah, if you increase your velocity around a turn, if you speed up around a turn, you're going to increase V, which increases your centripetal force. So usually, most people know this, you really shouldn't speed up too much around a turn. You don't really want to pass people when you're turning. You pass them in a straightaway usually, especially on like a one lane. Ever been on like a long one lane road? Like on US 100, I think it is. It's like just across the country. It's one lane. You only pass when there's a straightaway, so you can see A, and because when you go around turns, you're increasing your velocity to pass, which causes you to feel more force on the car.
Yeah, if you accelerate
What else?
down.
Besides velocity, what else is in the formula?
Distance.
R.
Radius.
Radius. Distance is the other formula, right? That's what R and the other one. Radius. So where's the radius, people? In this diagram, where's the radius? How could I draw the radius? Isn't this the radius right here? Isn't this the center of the turn? And I'm going around a turn. This is part of the circle here. Finish the circle off. Finish the whole circle. You see what I'm saying? That's the center. So what should I not do to the radius?
Make it shorter.
Why should I not make it shorter? What happens if I decrease the value of R, Tristan?
Then the force can be higher.
Yeah, the force goes up. Think about it. Remember, if you decrease the denominator in a formula, it increases the effect on the problem. It has the opposite effect of the numerator. It's like this. Ready? Take the number 10 and divide it by... Or take the number... Let's start with the number 12. Take the number 12 and divide it by the number 6. What do you get? Okay, you get 2. But then take the number 12 and divide it by a smaller number like 3. What do you get? So what happened to your answer? It went from 2 to 4, so it went... So when you decrease the denominator from 6 to 3, it had a double effect on the actual answer. So if you decrease the radius, if you decrease this, it's going to increase the force felt on your car. Well, the only way to decrease the radius would be to change your lane and move in, right? So when you're going around a turn, you shouldn't change lanes inward. That's the result of it, really. Because it would put more force on the car. It could cause your car to slip if the traction in the tires couldn't resist that force you're feeling. So when you're going around, especially like on roads that, like in the wintertime, if there's like a little bit of snow on the road, or even if it's raining, when you're going around a turn, like a significant turn on a highway or a road, you shouldn't really move inward in lanes. If anything, you should move outward, and it lowers the force because it increases the radius. And this is stuff, I know it's weird, but I do think about it when I'm driving. But it makes sense. It does, logically speaking, right? You wouldn't accelerate because you probably just don't do that. You don't speed up around turns. But a lot of people change lanes around turns. You shouldn't really change inward lanes. Just a random example. What are you going to say? Here's your hand, huh?
No, that's why you have all-wheel drive tires.
Oh, yeah. That's true. That's why you have all-wheel drive tires. What else? Do you want to do more examples? Do you want me to give you guys some time to work on the problem sets? How much time is left? It's 5 minutes left.
What happens to working on the problem system?
I'm sorry. We just reviewed and kept talking.
Okay.
There's only 7 problems. It's like if you do it with a partner, it's 3 each, really. 3.5. And none of you guys all do it. I know you all split it. I'm not stupid. Let's be honest.
Not all.
You do the whole thing? You both do the whole thing in your group? I was gonna say.
Do we get one bonus point if we do it ourselves? How about a point?
You'll probably get a better grade on the test if you do it all by yourself, or maybe, but I don't say you have to do that.
How
It's up to
about
you.
$0.5 to do a little dance?
Yeah, but sharing is caring.
Sharing is caring? What is that? Oh, sharing, like, meaning working on with a partner. No, I encourage you to work with a partner. That's what I encourage at the beginning of the year, but I encourage you, like, kind of both to do it and check each other's answers and submit one of them. But it's usually 2 different handwritings, 2 different people splitting it, but that's fine. It's up to you to choose. Any other questions? We have like 4 or 5 minutes left. You could start if you want to do a problem set problem, if you have it. Some of you took pictures of the textbook, so you can do one if you want. Nothing else? Yeah. All right.
Yeah, what do we next?